Okay, our next speaker today will be Bert de Waele. He's going to be speaking on structural data. Bert is from Fortescue. He's Perth-based mapping geoscientist working with Fortescue on international exploration projects. His career spans over 30 years and includes mapping work with geological surveys, academic research in the field of global and regional tectonics, and during the last 15 years or so, conducting structural mapping in the exploration and mining industry. Please welcome Bert.
Thank you. I've been giving this shift just after lunch, and we're going to talk about structural data. That's not a good start, is it? Unfortunately, when we talk about structural data, I'll have to take you a bit through structural geology as well. So it's getting even worse. The talk is basically in two bits. The first bit is going to be, like, call it structural geology 101, but really compressed, so not a lot of detail in that. And we'll talk a bit about how to collect structural data from outcrops and core. And then hopefully, if there's time, within an hour we should have time, a few examples of use of structural data, I think, in a real life sense. Actually, I can. So in my definition, structural geology is a branch of geology that deals with the form, arrangement, and internal structure of rocks, but also with the deformation history of rocks, right? So the geodynamic side of it. Measurements are collected from planar and linear features that you see in rocks, and those features come about as a result of that deformation, of the deformation systems on it. The feature that you measure, these lines and these planar features that you measure, foliation, cleavages, lineations, not only tell you something about the geometry of the rocks you're dealing with, but also reveal information on the geological history and the processes that those rocks have enjoyed. And one of those processes of main interest for us is obviously mineralisation. So the data you collect from structural features in the field or on core is incredibly important for you to strategize what you're going to do and for you to identify opportunities where they exist in terms of mineralization. The correct identification, and I put it in red because that's actually the most difficult bit. The correct identification of what a planar or what a linear structure is and what it means is the difficult bit of structural geology. That's the stuff that you can see on an outcrop with 3 or 4 structural geologists not getting to an agreement on whether it's left or right and stuff like that, right? So that's the most important thing. Actually measuring a plane or a line with a compass or with a protractor or with a chronometer or any of those instruments is as simple as it can get, right? It's just a method and then you just apply it. It's really simple to measure the things. Is interpreting what a planar feature or what a linear feature mean. That is the hard bit. That's what real structural geology is. The fundamentals of it here, this is why structural geology, one of the main reasons why, and we're, I think, most here in the gold industry, this is why structural geology is so important to us. This is basically the mineral systems approach kind of method that was taken over from the oil industry, which you know, basically the method is that you have to dissolve your metal of interest, let's call it gold in this case, from its source zone or along the path. Then you got to transport that metal that is now in solution in some hydrous fluids through the crust, through rocks, and rocks are not very porous. And then you have to get to a trap site where the, you know, for whatever reason, pressure drops or geochemical imbalances, your metal drops out at the deposition site, and then you have some outflow, right? So the main problem there is that, well, several metal concentrations in rocks, as well as in the fluids, crustal fluids, are incredibly low. You're talking about ppb to even lower sometimes metal concentrations. So for you to be able to transport metal into a trap site, your eventual deposit, and get economic values out of that, you'll need to transport a hell of a lot of fluids, a hell of a lot of metal in those fluids, right? And the second problem is that permeability I was talking about already. Rocks are inherently not permeable at all. So to move those large volumes of fluid, you either will need a hell of a lot of time to do it, or which we have, geological time, but you also need to try and get your permeability up in rocks. And what's going to do that, the main thing that's going to do that is going to be faults and shear zones. That's where suddenly permeability will go from almost zero to orders of magnitudes larger. That's the only thing that's going to be able to move crustal fluids through rocks. So a fault that moves fluid, but then the fluid crystallizes stuff in it, the quartz and carbonate and whatever else in it crystallizes, will stop being permeable immediately. So it's not enough to just have a fault or a shear zone. That fault and shear zone will have to be active for quite a long time and reactivate all the time to reopen that permeability. You need a positive feedback loop. Otherwise, the whole thing just grinds to a halt and you won't have a mineral occurrence. You'll just have an interesting small amount of metal somewhere, but not of interest from an economic point of view. So faults need to remain active. And then faults are never, in books we read, they're planar features and straight, and they're always straight lines on a map, but faults are actually quite complex features. And those complexities along a fault, bends, branches, jogs and steps and terminations of faults are actually the places where you have a lot more permeability, hence you'll have a lot more fluids moving into those spots, and eventually you might have a lot more metals associated with those spots. So it's important to understand the geometry of the fault and what the fault looks like along its whole structure for you to be successful in actually finding mineralization, economic mineralization. It's not all about faults, like I said. The deeper side of a fault, where you get into the ductile part of the crust, where things are not brittle anymore and don't fracture and produce a fault, you'll actually produce shear zones. Shear zones are the ductile equivalent of a fault. Shear zones are very important as well, again, because they move fluids, and again, because those are going to be the trap sites for your mineralizing fluids. If the shear zone is active when you have mineralizing fluids around, obviously. And there's also things like this, like strain shadows along these budinized kind of quartz veins where the sulfide clearly accumulates. That's probably also going to be a site where you have higher grades of whatever metal you're looking after. This is at a micro scale. And I took this picture, I think, from Brad Davis, this Olinda Gold Bible, which is interesting to look for on LinkedIn. But those sites, will, because geology is fractal, will also be expressed on a very large scale as well, on a deposit scale and even on a more regional scale. So those kind of features are important. And then the last thing I've said there as well, when you fold rocks as well, there'll be areas of high strain within a fold and areas high stress and low strain. Again, those high strain zones is where you'll have the ability of fluids to move and concentrate. So those things, the fold hinges, are going to be controlling your mineralization on a very small to a very large scale. So deposit scale controls of things like gold are often related to shear zones and to fold axes. So measuring, identifying those things in rocks, like I said, geology is fractal. If you find a small lineation on an outcrop here, that small lineation will be able to be expressed on a regional scale as well. It'll actually be the same linear, arrangement on a regional scale, which means your ore loads might be oriented along that small lineation you've measured on a core. So it's really important to understand it, to find it, to measure it, and unfortunately in the industry, gamma or lineation measurements are not that common, and that's a real shame. And I'll be hampering on that during this talk, I guess. It's one of the main frustrations. Let's talk about cleavage and foliation. That's one of the main things we measure, so just a planar feature that are penetrative and cutting through rocks, and they form because a stress field is there, and minerals that are platy or that are elongate are going to try and orient themselves perpendicular to that stress field to try and distribute it over as large an area as possible. That forms, in the end, a facility or a cleavage in the rocks, which you can see as a penetrative fabric in rocks. Often these stress regimes will also start deforming rocks, and then you basically start folding rocks. The first crustal shortening is going to be taken up by folding, and that folding will be associated again with a cleavage that is parallel to those minerals that all try and orient themselves perpendicular to what they call the sigma 1, basically the main compressive stress. But the whole thing deforms, right? And those cleavages are often not always, but often parallel to the fold axial plane. So when you find a cleavage and it's fairly consistent across a region, you can almost start guaranteeing, it's not always the case as I was saying, but that your folds are going to have the same geometry and the fold axial plane is going to be vaguely parallel to that. They are divergent or convergent sets of cleavages that form the fold. But in many cases, they actually almost get parallel to the fold axial plane as well. So something to keep in mind of, not always the case, but something to keep in mind. There's a few examples from somewhere in Ireland, I think. A fold on the left-hand side, which is also showing a discontinuity. If you get your crustal shortening to exceed what rocks can do in terms of deformation in folding, when that folding cannot accommodate the crustal shortening, you'll start breaking the rocks and things are going to start breaking apart and forming either reverse folds or thrust folds. That's how you accommodate further crustal shortening if that folding itself can't do it. So folds and thrusts or reverse folds are actually part of a spectrum of what the rocks do in response to crustal shortening. And when you find a fold, you have to start thinking about geometry because in the end, knowing how that fold sits in space is going to be important for you to either plan your drilling or to target your high-grade loads. And one of the first things you do is just check whether a fold is symmetrical or asymmetrical, as in this diagram. You can also use the terms, and I'm sure you remember those things from university days, antiform and synform, which doesn't take into account the younging direction, or anticline and syncline, which does take into account the younging direction of the folded units. And then you can predict what is in the core of an anticline or the core of a syncline, etc. You can look at the interfold limb axis, the angle between the fold limbs, and call folds gentle, which are when you have limited crustal shortening, to tight, to extremely tight, and eventually isoclinal, right? So that's just the interlimb angle. That describes the geometry of a fold to some extent. The next thing you can look at is the fold axial plane, which is the plane which holds all the maximum curvature lines on each of the folded layers. So you find the area where the maximum curvature is, and you generate the plane out of all those lines. I'm saying plane, it's actually a surface, almost never a plane. But depending on whether that plane is upright or inclined or up to recumbent there, you'll be calling these folds a steep, upright, whatever. And then you can call the open or gentle or isoclinal there. If you look at the fold axis, which is the axis itself, you can start looking at the plunge, and then the plunge is either gentle in one direction or steep or vertical, right? If you put all those things together, you can describe your fold in this diagram there, and you can start combining all those things and call a fold a steeply inclined, isoclinal, north, blah, blah, blah. You just basically name your folds depending using that diagram. Nature being nature is always a bit cruel. Fold axes are never straight. So if you either have a secondary fold event that overprints earlier folding, your fold axes are going to go all over the place. So using that nomenclature only actually works when you have planar fold axes and mostly in one deformation event, one folding event. But if you do find these things, you can call them culminations and depressions if a fold axis goes up and down. And in extreme cases and in very plastic rocks, especially carbonates, you have to be careful of, and also in very high-grade terrains. You can also find that the fold generation is different. The progression of the fold train is different along the fold axis, and you can start forming these sheet folds, which are looking like a sheath, and then everything becomes really difficult, right? So, it's not always that easy. And like I said, if you have more than one deformation event, then the diagram on the left there shows you the type of folding interference patterns. They call type 1, 2, and then 3, and then you have these O and blah, blah, blah. These originally were defined by Ramsey, but in more recent years, they've come up with more of those names. I normally don't use those, but you'll find them in literature. That's in 2 folding events. And then the photograph on the right is a photograph taken by Matt Painter, a colleague of mine in Namibia, which shows a rock that shows signs of 3 folding events. So things can get exceedingly complex if you're in a region which is polydeformed and has more than one tectonic event affecting it, especially if they're not coaxial, as is the case here, right? So things can get quite complicated. When it comes to lineations, and these are the most important things that you should try and look for in the field, should understand and interpret and then also measure. Lineations are incredibly important to structural geologists, yet undermeasured. These are the four main lineations that exist. Intersection lineation, which are in the intersection between two geologically meaningful planes. So not a break on a rock, which doesn't mean anything, and a layering, for example, that'll form a lineation that is of no real meaning to a structural geologist. But if the intersection is between an original layering and an S1 cleavage, then that lineation is probably going to be parallel to the fold axis of the F1 folds, for example. So when you see lineations on bits of core or on outcrops, you always look along the lineation and try and see if it can be related to folding, or if you think it's a fold, you try and see whether it is actually a fold plane you're looking at, not just some random break, right? Lineation is really important. Intersection lineations, you've got stretching lineations there as well. So if you're in a shear zone, you can actually start dragging all the minerals into one direction, and they'll form a lineation as well, which is going to be parallel to the sigma 3, which is your highest strain vector, which is going to be probably parallel to your ore shoots or the higher grade ore shoots. So quite important to recognize intersection lineations. Those are not always related to folding. They could be in shear zones. And then you have these lineations related to faulting, slicken lines, or they've got other names, grooves, striations. So these are lines which are developed on a plane that is broken, and basically two rock surfaces have scratched against each other, and you have a lineation that defines the direction of that movement. If you're lucky enough, there'll be steps on it as well, and then you actually get a sense of the movement as well. They're incredibly important things for especially faults that transact mineralization, post-mineralization, because that'll tell you where your high mineralized load, which is suddenly truncated, has moved to, and you know where you can drill. So incredibly important. And then fiber lineations are of less interest, but they give you a direction of opening on veins, for example. And sometimes they can develop as crystal lineations on fault planes as well, in which case they are important. These are examples of intersection lineations. In this case, an intersection between the folded units, so the S0s, which is the original bedding, folded in this form, and then forming a cleavage. The intersection between that cleavage surface and the original folded surface gives you an L1 intersection lineation. And you'll see on this diagram that that intersection lineation, wherever you see it, whether it's on the flank of a fold or in the hinge, is almost parallel, in many cases parallel to the fold axis. So they're incredibly valuable tools to recognize on an outcrop or on core, because it will give you immediately what a fold is going to look like on a regional or on your deposit scale. And the one on the right is basically an example of a crenulation lineation, which is basically an intersection lineation between one foliation and another foliation, which are often developed in very fine-grained rocks, which seem to record all the deformation that happens to them. You don't see that in very coarse gneissic rocks, but in schists and mudstones and stuff, deformed mudstones is very easy to see. So that gives you an impression of a secondary or a tertiary folding event that might have affected your region, right? So quality measurements on fold axes and intersection lineations are crucial in defining structural controls of the mineralized environment, because those stretching lineations and those fold axes actually give you the direction of your sigma 3, your highest strain component, which also gives you the direction of where fluids are going to be able to try and move through the rocks. And that eventually, if you've got mineralizing fluids around during the folding event, which is not always the case, but if it is, then your ore shoots are going to follow those fold axes. So it's important to recognize them, to measure them, and then to test your grade models to see if maybe you see some kind of orientation of your grade shoots in that same direction. Then you can say, hey, mineralization is together with that folding, because I'm seeing those axes are the same as what I see in the grade shells. You can also use it the other way around, where you just say, I'm going to assume my mineralization is related to that folding. Let's drill so that we intersect those lozenge-shaped core axes, so that we can get a better chance to intersect our mineralization. You don't want to drill along them, right? So they can be used for the mineralization plans on an entire body or on grade shoots, sometimes locally. In mine areas, you often have very localized strain influences, so these things apply for a regional scale. So you find a lineation, it'll be probably quite consistent across quite a large area, but within a mine area, it might be those small variations because of competency contrasts locally that change things locally and that produce an environment where you have a mineral deposit. So it's not always that simple, right? Another reason why lineations are incredibly important is because the moment you start dealing with sense of movement along shear zones, you do need to know the direction of your stretching lineation before you make that determination. This clearly states you need to be looking at a plane which is parallel to the lineation's in it, and is perpendicular to the foliation, the shear foliation that you're looking at. So that large plane on the right is the one where you can do your dextral and sinistral kind of determinations. And don't worry, I'm not going to go in any more detail about this, but that's where you can do your dextral sinistral stuff. If you're doing it on any other surface, you're looking at the wrong surface and it's meaningless, right? So you need to see your stretching lineation. So very important features indeed. Faulting, as I was saying, if you're near surface, let's say down to 8 or something kilometers, you're in the brittle zone. This is all depending on moisture, pressure, rock composition, and phyllosilicates, which is the same as moisture. So there's a zone in between, underneath that, which is called the brittle ductile zone, where things can either break or be ductile. And below that, you're in the ductile domain. So below 11 kilometers or something like that. But they're essentially the same. Near surface, where rocks behave not like toothpaste, but like rigid bodies, things are going to break, you end up making faults and joints. When you're actually below that brittle ductile zones, you'll be having a shear zone, which is the equivalent of the fault. And in between that, you can have hydro. And faults, again, this is from university, but it's just terminology, can be defined as normal if it's like the diagram there on top, can be reverse when the hanging wall moves up the footwall, can be sinistral or dextral if it's a lateral movement along a fault, and can be anything in between. So the terminology you use to describe a fault have to be based on the lineations you found and on the direction, the sense of direction that you've determined from those lineations, or sometimes marker horizons, but I'll show you in a few moments that that's sometimes a bit critical and difficult. When you look at faults, faults will tell you immediately, just like faults do actually, a fault axis is always going to be parallel to the sigma 3, and perpendicular to that and perpendicular to the fault axial plane, you'll have the sigma 1, always with faults. With faults, if you got normal faults, your sigma 1 is vertical. If you got reverse faults, your sigma 1 will mostly be horizontal. If you got dextral or sinistral faults, your sigma 1 is going to be at an angle to your actual displacement, sinistral or dextral. And these things are important because once you know the sigma 1 direction, the main compressive stress, if you take a book of paper and you push in that direction, it'll open up like this, right? The leaves are going to open up like that, which means your veins are going to be oriented parallel to the sigma 1 direction in a lot of cases. Again, this is grossly simplified, but in general terms, once you know the sigma 1, you should be able to make an educated guess of the orientation of your vein systems. So recognizing what a fault is gives you those directions as well. Recognizing what a fold looks like gives you those directions as well. So quite important features. But again, nature being nature, nothing simple. This is just a block diagram I got from the internet somewhere, I forgot where, but shows that faults are very complex beasts. And this is very clear in underground developments where you can take a model from a mine geologist, says level this, you see the fault there, that same fault on level that, level that, level that. The fault will look different on every level you look at it, or can look different on every level you look at it, depending on the type of rocks it cross-cuts, depending on the depth. So especially if you're straddling that brittle and brittle ductile zone and a whole sorts of other things. So there's a lot of complexity to faults, and trying to understand what a fault looks like, geometry of it, where the bends are, what the movement on it was, and then finding out where the releasing bends, the compressing bends are, One is going to be sucking fluids, the other one is going to be pushing fluids out of it. All those things can become important when you're actually doing exploration for a hydrothermal mineral deposit. Again, you got to be able to prove that a fault is active during mineralization, obviously. If it's post-mineralization, the direction of a fault movement is still important because it's going to cut your mineralization off, and you still need to figure out where I'm going to put my next drill hole to actually find back my bit of the chute that's been moved either up or down. Yeah. Few examples, again, one from Ireland somewhere. This looks like a normal fault. You can clearly see the black unit there dropping down on the hanging wall. On the left-hand side, you see an example of a typical shear zone. Now, the shear zone shows you a dextral sense based on those drag faults. Now, from experience, those kind of drags are a lot more reliable as shear sense indicators than just the visual offset on a brittle fault like the one on the left-hand side. If you haven't seen a lineation on the fault plane, so you don't know what the sense of movement is, you actually do not know what that fault is. It could still be a reverse fault or a dextral or a sinistral fault rather than a normal fault. This is just a diagrammic example of that. It's already shown as a normal fault. The red line there on the left diagram there shows it looks like a dextral displacement. You see the marker unit, the yellow one, has moved to the right. If you stand on the southern block, you can see that thing move to the right, right? If you look at the plan view on the bigger one, there's actually a normal fault on there. So what actually happened, this whole thing is an antiform. And what happened is that whatever was south of that normal fault has moved up. It's a reverse fault. It's not a normal fault. And as a result, you've got this apparent displacement of your unit to the left at the bottom part and to the right in the northern one. So actually, this is just a reverse fault, right? So take-home message there is offset marker units can be useful in figuring out whether a fault is reverse, dextral, sinistral, or normal, but you have to look for lineations, for the striations on your fault plane to be able to see what your direction of your movement was. And that's what a fault plane can look like. These two blocks have moved against each other, and you can clearly see from the steps on that fault plane itself. You can feel that in the roughness when you touch it. Sometimes you can use a hand lens to actually see those steps. They will prevent you moving that rock against the steps. So you know the last movement on that fault was with the steps, right? It's actually very logical to look at it. Take-home message there is that's the last movement on the fault. In many cases, that'll be the main overall movement of the fault. Faults are not things that happen in one go. It's probably thousands of earthquakes that form some of the faults that actually host gold or other mineralization. And most of the cases, the last movement will be synthetic with the overall movement of the fault, but you can get unlucky locally, right? So you don't want to base a whole drilling program on one striation and one of those steps on one of your core things. You want to try and build a story. Locally, it might be the other way around. So quality measurements of fault-related lineations, crucial again in defining direction of movement along the fault. The steps are what you'll need, or in shear zones, shear sense indicators along the shear are what you'll need to be able to figure out the sense of movement on your fault, right? So it's come back quite a lot, these lineations. All right, so veins. Veins very important in our world, I think. Not in mine, I work in iron ore now, but in the gold world, definitely important. Veins record the passage of fluids through rock, right? In fact, not the passage, the fluid actually stagnated and crystallized and you have a vein. So veins are the position sites as well, because those fluids, when they don't feel happy or when they cool down, will drop out whatever metal comes with those fluids. And they're also volume compensators. So basically, where you create volume, the whole thing will act as a pump that sucks in fluids. The fluids will move in and you end up with the veins localized. Veins can also be fluid barriers. If veins predate mineralization and they're thick enough, there'll be a barrier to fluids that go through it if they don't break. And veins can also be strain localizers. So when deformation happens and you got big competent quartz veins or dolerite dikes or whatever it is, then they will actually control what the stress field does around those very competent rocks. So, you know, you got to think of veins as two different things, either the stuff that is going to bring you the cash and the money and the gold, or things that are going to maybe prevent your fluids to get to the place where you want them to be. Again, nothing is easy in structural geology. You can basically classify, there's lots of classifications on veins, but I just see two types of veins. One is extensional veins, and another one is shear veins. And then there's anything in between. So extensional veins are parallel to sigma 1. So basically they'll be parallel to your main veins, and shear fracture veins are basically where you have shear, and they'll be normally at 30 degrees, but there could be anything lower than that as well. That's what these things look like. On the left-hand side, you've got a shear vein. Everything's parallel to the shear zone. Next to it, you've got an extensional vein with the quartz or carbonate crystals at right angle to the opening of the vein, so that one just opened and filled up. And then you got these extensional array, which is basically at about 30 degrees in its shear zone and gives you the sense of shear if you've seen a lineation on those shears. And then, of course, at a more near surface environment, you can get stockworks, which are basically irregular sets of veins that form in a brittle environment, and then breccia veins, which are associated with breccias. All those could be important because veins are often late phases of hydrothermal activity and often have all the incompatible elements and all the juicy stuff we're after with them. So when they crystallize, you might have something that's worth money. Now, to understand veins, unlike other things in structural geology, where you can just measure something, a dip and a strike or a plunge and whatever it is, with veins, things are a bit more complex. Veins have to be described in terms of their geometry, which is the vein direction, which might be a planar feature that you measure, or a lineation for the plunges that you see on veins. But the other things you need to mention in these is their composition. What is the mineralogy? What's the likely temperature and pressure that developed under? What's the alteration systems associated with it? And is there gold or any other substance you're interested in associated with your veins? Once you have identified the different classes of veins in a system, porphyry systems have that very well developed. In other systems, maybe less so. But you need to understand your paragenesis of your veins. This is an early vein set, has no metal in it, and is typically just quartz. That's a later vein set, that's quartz carbonate, and actually has molybdenite and some gold, but it's not economic. And then we got a third set of veins, and these are the ones we're really interested in because they've got all the goodies, right? And the direction is mainly that, but it's a combination of all those things. So when you work on veins, you normally need to not just have a structural geology hat on, and I am a geologist, I can do all other things. I'm not just a structural geologist. You need to be able to put the alteration systems together, the mineralogy of the vein, as well as the structural geology and the geometry of your veins. And that leads to these vein paragenesis, which you normally put into a regional context. So you can, at the end, say the gold comes in after the first deformation event and in the early stages of the second deformation event, for example. And then we have a late gold in a third event or something, right? So that's the work involved with that. All right, that was structural geology 101. We got through that. All right, measuring. Measuring, I brought some compasses here, but I didn't bring them to the top. So measuring happens with a compass, or when you're working on core, can happen with a compass as well. Other tools, which we'll get into in a minute. We're all familiar with this, and we've all learned strike and dip measurements with compass. But the main thing you want in a geological compass is a scale that goes from 0 to 360 for the azimuth, and then a scale that goes from 0 to 90 on the dip for the dip measurements, and a bubble. Why do you need a bubble? Because you need to find the horizontal on your compass, which will give you a dip direction. If you haven't got the bubble, you're basically clawing in the dark. If you got shallow features, you'll be fine. If you got steep features, you'll be really in trouble if you haven't got a bubble on it. All right. So the compass at the bottom there, which is silver, I think, just for mountaineering or something, has a scale that only goes to 60, doesn't have a bubble, so you can't use it for geology, or you shouldn't be using it for geology. Lots of compasses around. The left one is a Brunton, which I used to use before. Now I've gone to the one on the right, which is a Breitling. They're fairly heavy in terms of cash requirements. They cost about $1,000. But my first Brunton lasted me for about 15 years. So if you take care of them, they'll last not for a lifetime, but almost a lifetime. And they're really, useful. You can see on this compass, you got basically the gradation on the dip on the side, and the Breitling, the blue one, you basically see it at the top. There's the dip measurement straight in one measurement, so you can do it all in one go. You still have the option to use the clinometer, which is within the compass as well. Now, what I've learned, and I'm sure it's the same here in Australia, I was trained in Belgium. They taught me the right-hand rule and strike and dip, which I'm urging you to forget right now. Yeah. So the best thing to measure is dip and dip direction. They're just two numbers, and there's no ambiguity with it. You decide which direction something dips in, and you measure that direction. We've got a number which is the dip, 32 in this case, and a number which is the dip direction, 152, which happens to be southeast, but you don't even have to think about southeast anymore. So all that mental stuff that you have to do when you do right-hand rule, and this is dipping towards there or there, is all gone. And the bias of, am I using this strike or this strike? It's all gone. It's just dip direction. The good thing about this as well is that a lot of software packages will actually assume that you're using this, and you might be able to strike or the Canadian method or whatever else you want to use, but this is the standard method now. You still need to know what the right-hand rule is, which means that you're taking the strike, and then to the right of that is where your dip should be. That's the right-hand rule. You still need to know it because a lot of historical data you'll be dealing with might be that strike and dip. Yeah, and how you measure it is by putting the compass, but anyway, it is practical. Now for lineations, same thing, but you call these things plunge direction. When you translate that to French, they actually don't have a name for plunge. So for them, it's all plunge actually. They don't have a name for dip is doing, but we use different words. Plunge direction is for lines. When you say something's got a plunge and a plunge direction, it's for a linear feature, never for a planar feature. And how you measure those things, you construct a vertical plane which holds your lineation, and then you measure the direction of that lineation towards me while I'm holding it like this, right? If you don't do it for shallow lineations, you'll be all right. You can just say, that lineation goes like this, I'm measuring it, and you got it, and then you measure the plunge, of that lineation. But for fairly steep lineations, please use a notebook, put it on it, rotate it while it's in the lineation until you got a vertical using your bubble and your compass, if you got a proper compass, and then measure the direction of that lineation. Incredibly important to get good, reliable lineation measurements. There's no good measuring something if it's plus or minus 20 or 30 degrees out. And for steep lineations, you really have to put your notebook on it, right? You measure a plunge and plunge direction, very easy. Measuring on core. Why people would do structure, non-vertical diamond drilling and not orient core is beyond me, to be honest, right? You're spending a lot of money doing diamond drilling. To spend an extra 5% of your cost just to rent a machine, it's all in line now. You don't have to interrupt drilling for that much. So the cost differential of not orienting your core is actually negligible. Your offsiders will spend a bit of time trying to, put a line on, and that's about it, right? So please, if you do diamond drilling, orient your core. Because when you have oriented core, you've got a fighting chance to get data out of it, structural data, which is going to be critical in whatever you do after that, right? The 10% logging and handling cost is just because you got to spend a bit of extra time chasing for foliations and chasing for lineations, measuring them, maintaining them in a database, and then also interpreting them. But that's all good stuff. It's good data if you're doing a good job, and the interpretation is going to be of extreme value later on, especially in structure controlled mineralization. Okay, the principal objections to people still not doing it is we don't have experience with those tools. They're incredibly easy to use, by the way. Drillers get on top of it in basically looking at one video and then just doing it. It's very simple. And then a reluctance to change. I think things are changing. You know, I've been in the industry for 30 years. It's been a long time. But in the last 10 years, I've seen more and more people doing oriented core. So it is changing. But there's still a lot of people that are drilling, not putting these lines on it. So a decision not to orient core, I think, has to be really justified. If not, if it's a vertical hole, you can understand, but if you're inclined drilling, then you should orient it. And that's the reason why you've got a chance to actually come up with something that is a bit geological rather than just connecting dots on a section, as is the case there. You can see the structures, you can measure them, you know what your orientation is going to be. You can pull it together with your geological knowledge a lot better than when you don't have the knowledge. This is just one simple example that I stole from SRK, I think. That's the stuff you can see on core. I think you've all worked on core. Basically, you see the same on core as you see on outcore, right? Only better. You've got it in 3D. So you can see shear zones, folds, granulation cleavages in the middle and the top. You can see fault planes with striations on it and steps. You can see shear sense, the one in the middle at the bottom, shear sense indicators. But again, only do this if you know where the lineation is on your shear plane, on the S plane. Once you know the lineation, you look at right angle to that lineation. Otherwise, whatever you're collecting is going to be wrong, right? And then, yeah, you see several foliations, really easy. Beware with core orientation that everything hinges on that orientation line. If that orientation line hasn't been put properly by either your offsiders or by your geologist that is with the rig, I don't know what your systems are, but if that line is not properly put, or if the mark on the core at the end of the core isn't properly put, then you lost. Somebody can still put a line there, but whatever you're going to measure from that line is going to be really off. So when you do these kind of activities, always look at the start of your run or the end of your run, whatever your orientation mark is. Have a look at the orientation mark, satisfy yourself that you're happy with that orientation mark, and then have a go at re-puzzling together the core and see if you're happy with the orientation line itself. It won't take that much time to do it. And then at least you can have some confidence. In databases, often it's indicated how confident someone is of the orientation line. You can kind of use it, but when you work on core, just always quickly check. Very important, that one. Once you got that line, you know how the drilling was done, hopefully, because you plan your drilling campaign. Let's say it's 70 degrees towards 270, towards the west. You can take one of those rocket launchers, they're called, and you can basically reorient the core, the whole instrument, so that your core is now sitting at 80 degrees or whatever it was, 70 degrees, towards the west, towards 270, exactly. And then it's like an outcrop, and you can just go completely bonkers with your compass and with your notebook and start identifying foliations, planar features, faults, lineations, whatever you want, and measure it. Very time consuming, but you do get an immediate sense of what happens, you know, what is your geometry of your whatever you're measuring, right? But in my experience, you can do the same by just taking the core and just saying, what was this drilled at 70 towards the west? Where's the west this side, 70? Oh, right, you got the same idea, right? So it doesn't take that much time to get it in your head, whether you've got a very flat lying foliation or a very steep lineation towards whatever direction before you start measuring. The other way is using these alpha, beta, and gamma measurements. I urge you to go to Rod Holcomb's website and download his booklets on it. He's got guides on these things, very well explained. The protractors are there and the strips that you can use. I use strips. I'm not a very complicated person. I just print out the strip, plastify it, and use a protractor, and I measure everything with that. No kilometers for me. I'll explain why maybe. Anyway, this is the core thing. You can also use just a sandbox rather than paying money for that instrument. That's very simple. But this is alpha beta. So the alpha angle, I think you all know that, you probably have done it. The alpha angle is just your angle, your maximum dip angle basically, which is perpendicular to your beta mark, which is where the ellipse goes horizontal on your core. You got this ellipse, the long axis of that will have two intersections. The one that is looking downhole in the orientation of your core is the down one, is the one you'll mark as the beta mark. That's where you're going to put your protractor and you can measure your alpha on, right? That's the alpha. The beta is just your angle, clockwise looking downhole. With the strips, you don't have to think about it. You just put the strip on it in the right direction and you measure between your orientation line and the beta. And the gamma is basically another angle between the beta mark you've got and your gamma. Now the gamma can be the lower gamma if it's just a lineation with no direction, so it's not a striation. You always do the lower gamma, the down plunge direction of your fold axis, for example, looking down core. In faults, when you have a striation and there's a sense to it, you can actually do the up angle gamma, right? That gives you the sense of the direction. You just mark that in your database. But very important, it's not always the down gamma. So what's difficult about gamma and what is scaring structural geologists or pretend structural geologists to measure a gamma? Oh, it's too difficult, sir. It is not difficult at all. It's just another angle. Instead of between zero and gamma, zero and beta, you just go between beta and gamma. That's it. The only difficult thing is finding a lineation, knowing what it is, making an educated guess what it is, and then measuring it, right? So before you measure, like I said, you check the core blocks, the ori marks, the ori line, and look for these signs of core spin, which is the big enemy of orientation devices these days. Gyroscopic devices are, that's the thing that can go wrong with them, is when you have an instrument that is too hot or too cold, so it loses calibration, or when you have core spin within your barrel as people pull it out. Core spin is recognizable, so you can actually look at it. And you mark the downhole direction and the depth if needed before you lift things out. I've seen so many people lift the thing out, they go away, they measure it, and then they come back and they put the thing upside down or something, you know, so you just mark the thing. It's good for you to mark something before you get it. Identify the structures in vein you want to measure, think about them, interpret them. If you don't know what something is, if you measure it, put a big comment in big capital letters. I don't know what this thing is, right? Otherwise, you end up with shit data. You need to understand what you're measuring. You can still measure something you don't understand, but then have discussions so you can try and start thinking, is this a fold axis? Or is this lineation something else? A stretching lineation or whatever. So keep an eye out for lineations. I keep hammering on about lineations. Yeah. Measuring, you orient the core in the right direction, so you can get a first idea. Okay, well, this looks like it's a very steep bedding or whatever it is you're going to measure. Then you mark this lower apex, which is the ellipse on it, the lower one looking downhole. So that's the lower one. You mark that one. If that one's the lower one, because it's the other way around, you mark the lower one. And then if you got a lineation on it, you either do the upper gamma or otherwise the downhole, the lower of the two gammas. If it's almost the same, it means it's a sub-horizontal lineation. So it doesn't really matter that much. Just do your best with that. And then you measure them. From the ori to the beta mark for a beta angle, and from the beta mark to the gamma mark for your gamma angle. Done. And then you do the alpha. Simple. And while you're doing it, try and have a piece of software ready, either an Excel spreadsheet that can convert everything from your known drill hole direction and the alpha, beta, gammas. It'll give you a dip and dip direction or a plunge direction, so that you can just copy and paste that into a stereo plotting piece of software, and you get an idea of whether you're getting good data. Because if you have issues with your orientation line, you'll pick it up quite rapidly. But if you're just going berserk for a whole day and measure alpha, beta, gammas, and then at the end of the day, put it all on and notice that there's a serious problem with your orientation lines or with your data, then you wasted the whole day. So just do it on the fly if you can. There is a piece of software for people who use Android phones. It's called Alpha Beta. I think Alpha Beta by Erwin Lebrun from SRK Consulting in Canada. He's now in Australia, which is, it's almost for free. It's the price of a coffee, basically. And you can just basically plug in your dip and direction of your drilling, put your alpha beta, and it gives you the strike and dip, the dip and dip direction, or put your alpha beta and gamma, and it gives you the lineation straight away. So you can just basically keep a tab of what's going on if you haven't got an Excel spreadsheet for it. That's an example of an alpha measurement with a protractor in yellow. I don't know where I stole that picture from. And that's, again, an alpha measurement with another protractor, and then use those strips. The strips have a diameter, which is exactly the same as the core you should be working on. There's all sorts of different designations for core, NQ, 1, 2, 3, NQ. There's also HQ, 1, 2, 3, and some other variants of it. All those strips are available in Holcomb's document. You make sure you print it out at the right scale. Actually, it has the measurement of how much millimeters the circumference is. Measure it, make sure it's the same. plastify the thing, and then go off and measure with those strips. But make sure you're using the right direction, the right strip for the diameter of core you're working on. That is the same thing with the chronometer. With the chronometer, you need to, that's an American instrument, which only allows you to measure up to 5-degree differences. That's why I don't like it, both on the side, on the dip, and on the beta measurement. And also sometimes you have to put the core in the other way around to be able to actually measure a dip. And on half core, it's an absolute pain to use. Yeah. The second problem with those things is that they come in an HQ and an NQ variant. This is the NQ one, the blue one. The HQ is a black one, but it doesn't come in any of the other variants. So you can buy the converters for it, which are 3 metal strips you have to manually stick into the instrument to make it work with the other core, right? Most people don't bother, which means you'll be introducing a 5 to 10 degree difference in your measurements. So not as versatile as a strip, which is for free, by the way. These things cost money. All right, so measuring on core, you identify and describe the features. There's no point measuring something you don't know what it is. So first of all, try and satisfy yourself. You understand whether it's an S1 foliation or whether it's a fold axial plane or a fold axis, which type of fold is it, F1, F2, blah, blah, blah. Then if it's a vein, describe not just the geometry, but also mineralogy, alteration, relative timing. Take pictures. Put notes onto a notebook and on the core itself, mark everything and enter it in an Excel or use that piece of software I was saying on the Android phones to convert your stuff on the fly so you know you're collecting good data. And if you can, plot your data on stereo nets. I know stereo nets are a bit daunting, but they're very easy to use these days. You don't have to rotate things and use pins and stuff to do it anymore. You just drag and drop the thing in something like I use GeoOrient, which is a really simple tool, and Holcomb stuff again, really quick to actually see what your data plots like, and you can start picking up whether your plunges are giving you consistent data or not, what your general S1 fabrics look like, and whether you see folding in there. There's lots of things you can do with it. All right, so I think great timing. 5 minutes, so a bit more than 5 minutes. A few examples. This is the most common example. Once you've got some structural data, there's 2 examples from Canada. One is, I don't know, they're both syn or antiforms, I can't remember. If you got structural data on something like that, you've measured a few fold axes, you measured a lot of beddings or a lot of foliations, you've got half a chance to actually put your map together because you'll be able to visualize it in your mind's eye, you know, what you're dealing with. So in the left example, you can see the dip symbols, and I can't see from here, and I haven't got my glasses on, but you'll see whether the thing is a synform or an antiform. If you know the age of the things, you know it's a syncline or an anticline. You cannot put geological boundaries across foliations. Everything will be parallel to the foliations. If you got lineations with fold axes, you'll be able to define the plunges on these things. A very common thing. Structural data is absolutely vital when you're creating maps. In this example, this is a map from somewhere in Africa. And basically, we didn't have the airborne magnetic data at the time of the mapping. This is rainforest. You just have isolated outcrops left and right, measure all the foliations on them, and you can put these things out as disks in this piece of software called Leapfrog, which I'm sure you all know. And basically, the foliation measurements on all these disparate outcrops give you the idea that the whole thing is actually folded against probably a fault in the north of that picture. The other thing I picked up, you see this cross-cutting fault, somewhere about west, northwest to southeast there. In the field, we actually found joint fracture sets that were parallel to that fault. So that gave me more confidence to put a line there. When the magnetic data came and you saw the demagnetization and slight offset, I was very confident putting that fault. So structural data, again, incredibly important when you're creating a map. It is the base data you're using. It's not lithological data. This is where the BIF is. This is where it isn't. It's actually all the structural data that allows you to shape those geological contexts. If you're in areas with not that much data, and you got to make decisions about, am I going to drill, or can we use drill hole data, historic drill hole data that was provided. This is an area somewhere in Zambia. In that case, you could see the 2 small circles show you 2 dip measurements. That wasn't enough, so I went to the field and did a bit of mapping on the lower bit of the Rhone, the Mindola clastics. It's sticking out. You can actually collect some bedding data. use that bedding data, put it in Leapfrog, just assumed it was a planar contact that would go on forever. So you end up with a planar thing, and then I put the historical drilling in, which was just paper copy drilling, very old. The drill holes don't exist anymore, to try and assess whether those drill holes actually reached my target horizon, which is above the Mindolo-clastics. It turned that they did, and that the assays in them, if they would have transacted it, weren't that encouraging, so we could walk away, right? So very minimal data in this case, just a bit of playing in Leapfrog, and I'm definitely not a Leapfrog guru, but very simple to actually quickly use some real data as well as data from maps to make a decision and make a call on something. This is an example from the Southwest terrain here in WA, a gold project. I think it's somewhere shown which one it is. But that one was worked on by company geologists that measured a hell of a lot of structural data. They had a database full of data, all planar data, no linear data whatsoever, just foliations, shear zones, contacts, all sorts of other planar data. And that planar data, it's shown there, one set of data from that whole data set. They had a lot of codes for roughly the same kind of thing, so they would all plot in the same thing, but it clearly shows you that you got a shallow, sub-horizontal to a shallow northeast dipping set of strata. And the mineralization based on hundreds of thousands of meters of drilling actually show that direction of gold as well. So that's fine. I actually pulled out, this is EIS funded drilling, so you're free to go to the GSWA and actually pull out core and actually look at it. I did this for a training exercise at Fortescue, pulled out the core and just told the guys, okay, I don't want you to measure any alpha betas in isolation, measure a gamma as well. Try and find lineations for me, try and define what they are, measure them, and then we'll see what comes out. So they did that on only five diamond holes, right? Lineations from 5 diamond holes showed us a shallow plunge to the south. And lo and behold, if you look at the long section, which is developed based on grade only, not on lineations, shows that plunge. So imagine if that company, and I don't want to speak too bad about it, but if that company would have done oriented diamond core from the very beginning, maybe when EIS didn't exist, and would have done the lineation measurements, they would have been able to test the concept of whether the plunge of that gold mineralization in a high-grade granulite fascist terrain actually follows that plunge, and it does. So interesting data to collect, wouldn't you agree? And it's not that difficult, as I was demonstrating, alpha, beta, and gamma. A gamma is just another angle on, the angle between the beta and the gamma mark. It's very simple to do. I'm not sure if this is the last one. No, it isn't. When I say structural data, I actually kept it fairly, because I'm an old guy, real structural data, compass measurements, mapping, outcrop, and maybe core. But actually, when you look at drill hole databases, RQD measurements, incredibly valuable. When you got a big data set, a lot of people have collected RQD, which is routinely corrected by everyone. I'm sure everyone in the room has done rock quality designation measurements on core. That data can be incredibly critical in identifying fault zones and zones where there's a lot more rock breakage, basically fault zones here. And that might have an influence on either displacement of an ore body or on the ore body itself. Structural logging codes, obviously, we've touched on base on that. The fracture frequency, sometimes you get logging where you just say the frequency of fracturing, it's a geotech logging, it's a geotech thing, but that on itself can also identify clearly these two fault zones. So you don't have to go out and measure your alpha, betas, and gammas in the field. You actually can use those already collected simple data, just as fracture density or fraction frequency, to actually identify those things. These only work when you've got big databases. And historic databases sometimes are really amenable to that kind of analysis, because RQD data has been around forever, and fracture density is often collected as well. Really useful. And then obviously grade. When you look at a grade model or at grade in a Leapfrog model like this, you can see the grade is associated with something that might be a structure. You can go back to the core or even the RC chip logging and actually try and figure out, is it associated with the structure? What does that structure look like? So sometimes grade can give you some structural data as well, which is confident enough for you to actually develop a fault and model a fault in a 3D model. So it's not all about compass, outcrop, and measuring things on core. it can sometimes be something like that as well that gives you an edge in structural analysis. All right.